Hello everyone. Today we are going to talk about the chapter 1, Science and the Universe, a brief tour. We'll talk about the basic idea of universe, scientific method, and some good measurement we typically use to describe the distance in the universe. First of all, let's look at what is actually the universe. The universe is basically everything you can imagine. So that is including, of course, include our Earth, the sun, the stars, the galaxy, and of course also include something you're never able to see. For example, energies, and you may also heard about dark matters. So basically, universe, anything you can think about that belong to the universe. So you can see the universe is the totality of all space-time, matter, and energy. Can anybody imagine or anybody know how big is the universe? If you do a quick search, you will find that although we know universe might be the largest concept or things we can ever imagine, but if you look at its size, it is actually not infinite. The observable universe is about 19.3 billion light years across. Remember here in this description, I used the observable universe. The reason why we use observable is if we look at the edge of the universe to the other edge, that means there might be a part universe that beyond our observation. So that also means there might be a universe bigger than that. But the problem is that the universe, the range of universe we are able to observe is 19.3 billion light years across. How about the age of a universe? Of course, because universe include everything you can imagine, universe is of course the oldest concept you can imagine because everything basically appeared after the birth of the universe. You may heard about the Big Bang, right? So we use the Big Bang to mark the birth of the universe. So far we know the universe is about 13.8 billion years old. So 13.8 billion years ago, that exactly the time the Big Bang happened. However, nobody actually able to observe the birth of the universe. Later on, we'll talk about the human history in the history of the universe. It's a very tiny part of the time. So next, let's talk about astronomy. Astronomy is the study of the universe, and astronomy is a science. So if you know that, we'll talk about later scientific method. All the science will all based on the evidence. You may know that like a physical science, like chemistry and physics and biology, we can do experiment. But unfortunately, there's almost no way you can experiment on a star. To create a star by human being, observe its lifetime, and see how the star gradually run out of its fuel. So therefore, we talk about astronomy is basically the observational science. That means the evidence or the data are all based on our observation. So it doesn't matter you observe the night sky using your naked eye or you observe more scientifically use the telescope. Most of the facts or the data are from observation. And as well, because there's almost little control of a human being on how celestial object will evolve. Therefore, astronomy is also what we call historical science. That means we can only observe what happened in past. Other than astronomy, you may also heard about astrology. The difference between astronomy and astrology is that astronomy is a science which follow the scientific method. Astrology, instead, it is not a science. Now let's talk a little bit about the scientific method. Scientific method usually start with an observation. And when you observe a phenomenon for a couple of times, then you can, based on what you observed, you can make some prediction and finally come up with a theory to describe the phenomena. Of course, the more observation will test if the theory is valid. However, scientific theory must be testable and can be proven wrong, because there is no way you can rule out in future that might be an observation that cannot be explained by the theory. Let me just give you an example related to the astronomy. If you heard about the story that Newton actually discovered gravity by sitting on the apple tree, and an apple fall hit his head. So that is observation. I bet if the story is true, he probably observed a lot of times what happens when apples fall from the tree. It will always going down and hit the ground. So he make the prediction that there must be some force to make the apple go down and hit the ground. So later on, Newton developed the theory about gravity. If you look at the object on the surface of the Earth, you may notice that Newton's theory of gravity is valid for almost all of the observation. However, about 100 years ago, when Einstein tried to use Newton's theory of gravity to explain some phenomenal objects such as black hole in the universe, he actually found out that Newton's theory of gravity is not sufficient to describe the behavior of black hole. Therefore, Einstein actually developed his theory of general relativity to describe some of the phenomena that cannot be described by Newton's law of gravity. So you can see scientific theory must be testable and can be proven wrong, but they can never be proven right with 100% certainty. If you're familiar with the units or distance measurement we used in our everyday life, for example, you drive from your home to school, maybe it's 10 miles. And if you measure a person's height, maybe it's like 6 or 5 feet. However, in astronomy, numbers are very huge. So, for example, the miles sometimes is too short to measure any distance between celestial objects. So therefore, in astronomy, we're dealing with a lot of big numbers. Let's first talk about scientific notation. That's how we made it easier to write down a very big numbers. You can see the example I have here is 500 million. You can see there are so many zeros, right? So in scientific notations, we usually use a number that is between 1 and 10. Multiply a number which is a power of 10. So usually how I come with this scientific number, why I know is 10 to the 8th power. So basically, you know here is the decimal point. You start to move decimal point 1, 2, 3, 4, 5, 6, 7, 8. 8 times until you end to have a number that is between 1 and 10. And you count how many times you move the decimal places. So we move decimal places 8 times. So we have 10 to the 8th power. Let me give you another example. For example, we have, how about 6, 5, 7 million. How can you express this number in scientific notation? Remember, we start moving decimal places. So we move 1, 2, 3, 4, 5, 6. You should not stop right here. 7 and 8. You move decimal places until you will end to have a number between 1 and 10. So now it should be 6.57. So in scientific notation is equal to 6.57 times 10 to the 8th power. So that is how we use scientific notation. Although scientific notation will make it easier to express numbers in astronomy, but sometimes we still prefer do not always use 10 to the certain power, because this way, well, people will need to take some time to think about how big is a number. Therefore, in astronomy, we actually make some units that used to describe the distance. The typical distance measurement we used in our everyday life, if you know, that's like miles, yards, and meters, kilometers. And however, when we talk about the distance in astronomy, we usually use light year. For example, when we use light years, there's a lot of stars. It will just within 100 light years away from us. So instead of use 10, power of 10, we can just use a number. Let's look at how large or how big a light year is. So light year is basically the distance light travels in a year. In astronomy, we will tend to not use miles or yards. We are going to use meters or kilometers. So let's do a simple calculation to see how we can come up with the number of light year. So remember how you calculate the distance. You can use the speed of light. Speed of light, which is 3 times 10 to the 8th meter per second, right? And we need to multiply by how many seconds in a year. We know first we need to multiply that by 365 days in a year on average. most of year, and times how many hours in a day, which is 24 hours. Then we multiply 60 minutes in 1 hour. We haven't reached the second yet. And finally, we'll multiply 16 seconds in a minute. If you do the calculation, you will find out the result is 9.46 times 10 to the 15th meter. Okay, so that's all how we get the distance in terms of meter in light year. If you're interested in know how much miles, it's about 6 trillion miles of a light year. So light year is a very good unit to describe the distance between stars. For example, the nearest star from Earth or the solar system is about 4 light years away from us. Then we have stars 1,000 light years away from us. And of course, we have stars that are galaxy like 1 billion light years away from us. So you can see, even sometimes light year can be short when you describe very distant object in the universe. Another interesting aspect of light year is light actually need time to travel. And on the Earth, when we see the light, we feel that is instant because light is actually travel very fast, like 300 million meter per second. So that's pretty fast. Any scale on the Earth to the light, how fast light travel, you will observe things like instant. Every second, the light can go around the Earth about 7 times. However, if we look at the distance object, you can see the light actually takes some time to travel. For example, if we think about the nearest star, which is Proxima Centauri, the nearest star is about 4 light years away from us. And most of the case, we observe the star because we see the light the star emit. For example, if you look at the Proxima Centauri tonight, you see the light from the star. The moment you see, remember the light need to travel 4 years in the space before it reach Earth. Therefore, if you think about that, the light you're able to see from a star that is 4 light years ago already left the star about 4 years ago. And it takes 4 years to travel in space and finally reach Earth. So therefore you can see. And another interesting aspect that also means the light or the information we receive about the star is actually only deliver us the information about 4 years ago. What the star is undergoing, we have no idea right now. We have to wait another 4 years before the light that carry the information what happened on the star right now to reach us. So that is only for the nearest star, which is about 4 light years away from us. Think about there is a galaxy can be 1,000 light years away from us. That means the moment we see the light from the galaxy already left the galaxy 1,000 years before. So we actually see the light. We see what happened to the galaxy in the past. So that's why we talk about, because the light travel time, the observation into the past. You may think about, oh, that might be not a very good thing on one aspect, because we never able to know what is happening right now. But on the other aspect, it is a good thing because when we look at a star with different distance away from us, we're able to observe the past. We're able to see what happened in past. So therefore, the further the object away from us, the more back in history we can observe it. For example, if you have a galaxy that is like 10 billion light years away from us, that means the light actually carries the information of the galaxy that is 10 billion years ago. So that is very, very valuable because that might give you some hint about how the early universe looks like. And of course, if it's the star that is 1,000 light years away, that will carry information a little bit like closer or near the recent time. So therefore, when we look at the celestial object at a different distance, we're able to picture the evolution of the universe because some of give us information near closer to the birth of the universe, and some give us the information that closer or near the most recent time. We talk about the light year is a good measurement for the distance between stars. But if we are talking about the scale within our solar system, the distance between the sun and the planets are much, much smaller than 1 light year. So therefore, to be convenient, we actually will introduce another units we say, which is astronomical units, and usually we use AU to denote astronomical units, which is defined as the average Earth and the Sun distance. Why we say average? Because later you will learn that the Earth and the Sun distance is not always the same at different time of the year. 1 AU is about 1.5 times 10 to the 11th power meter. Remember, if it is still, although it is smaller than a light year, but this number is still much, much bigger than the typical distance we talk about on the Earth. So if you still remember the idea, the light travel time, that means the light will still take some time to travel this distance. The moment we enjoy the sunshine, the light already left the sun a moment ago. Now let's go ahead to do a simple calculation to see how long it takes for the sunlight to travel the astronomical units and before it can reach us. We can do is we can use 1.5 times 10 to the 11th, which is the distance, divided by the speed of light. And you will get that's about 500 seconds. If you divide by 500 seconds, divide by 16, so that is about 8.3 minutes. So you can see every piece of sunshine you are enjoying right now already left the sun about 8 minutes ago. If you look at the object in the space, just for example, the Earth and the Moon, their distance is actually far more or larger than their actual size. Usually, in order to fit a lot of objects in a picture, we put object closer so we can fit everything in a picture. However, if we draw the Earth and the small things here you can see is the moon together, use a real scale of their distance and their size, you can see there's almost like empty space between Earth and the moon. Next, let's take a brief tour of the universe. So we know we all live on the Earth. We all know now we have the ability to send a rocket ship into space. And what beyond the Earth? You probably know we are actually in our neighborhood. If you imagine Earth is your house, your home, and our neighborhood is actually the solar system. We have our neighbors of planets, and the sun is our parent star. If the solar system is a neighborhood, then for the even larger scale, we have a local stellar neighborhood. That maybe, I would like to say, maybe that is all the neighborhood in a city, and the local stellar neighborhood is actually a part in an even larger scale, which is, you can see our state, which is Milky Way galaxy. Like we live in Georgia, so you can imagine the Milky Way galaxy is Georgia. But you know there are some more than one state in a country. So the even larger scale is local groups of galaxies. So that means there are a group of several or more than 10 galaxies are close together. So we call the local groups of galaxy. Even go to even larger scale, we will have even larger scales cosmic structure. I'm going to invite you to watch a video called The Powers of 10. So see how we can start from a person and gradually increase the scale to the large scale of cosmic structure.
The picnic near the lakeside in Chicago was the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now every 10 seconds we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is 1 kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds. The day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1 million meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the Sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the Sun, followed by the massive outer planets, swinging wide in their big orbits. That odd orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This squares 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the Clouds of Magellan, 10 to the 22nd power, 1,000,000 light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we'll appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity, a rhythm that will continue all the way into our next goal, a proton in the nucleus of a carbon atom beneath the skin on the hand of the sleeping man at the picnic. Ten to the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power. Now we reduce the distance to our final destination by 90% every 10 seconds, each step much smaller than the one before. At 10 to the minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand. In a few seconds, we'll be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn. An outer layer of cells, felty collagen. The capillary containing red blood cells and a roughly lymphocyte. We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons make up the outer shell of the carbon itself. They appear in quantum motion as a swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the 2 inner electrons held in a tighter swarm. As we draw toward the atom's attracting center, we enter upon a vast inner space. At last, the carbon nucleus. So massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy.
And you can see from the video powers of 10, we not only go all the way to the larger scale of the cosmic structure, we also go to the opposite direction to go to look at the structure of the most small scales, which is a building block of everything, which is basically atom. You can see that what is atom? I hope you still remember the atomic structure. So basically, the atom is that you have a nucleus at the center and you have electrons go all around. Although the universe is large, but it's still built from the basic structure of atom. And here I give you an example of carbon atom, which is most important building block of our body, and which has 6 protons and 6 neutrons. And if you look at the universe from the small scale, what universe is primarily made from? What is most abundant atom in the universe? You can see that hydrogen takes the lead. So that is basically in 10,000 units of mass, how much is hydrogen? And the helium is a second. So if you know that the stars are made primarily from hydrogen and helium. And unlike the high concentration of atoms actually on the Earth in our body, the space in the universe, especially between stars, they almost have nothing. So they have very, very, very little amount of hydrogen or helium. And you can see the rest of the elements. Sometimes we call them trace elements. They all have very, very small amount. Even the most important atom for us, for example, oxygen and carbon, is much less abundant than helium and hydrogen. And one interesting thing, you can look at the structure of atom. Do you think it looks like how the planets orbit around the sun? So that is people found is that like unify of the structure in large and small scale. Now let's take a look at the time. We talked about the age of universe is about 13.8 billion years old. We scale the time down to a year, so use like 12 months to represent this 13.8 billion years. You can imagine roughly each month is a little bit over 1 billion years. So we mark the Big Bang on the New Year's Day, which happens on January 1st of the year. And we mark the significant events happening on each month. You can see that the Milky Way galaxy won't form until May, which almost like a half from Big Bang to now. And our solar system won't form until the September, which already mark like last a couple months in the cosmic year here. And you can see that the Earth pretty much formed at the same time when the solar system formed. Earth gradually gained its atmosphere around October, within the last 2 months. and we believe the first complex life forms around November, which is about 1 billion years ago. And what time actually dinosaurs appear? We're gonna have to expand the month calendar for December. And dinosaurs actually appear on the Christmas, which is December 25th. And to the same scale, 1 day later, mammals appear. And human actually, in this scale of cosmic calendar year, human won't appear until the last day of the year. So you can see that the human history is only it's only 1 year, 1 day compared to the 365 days of whole history of the universe. This is about I want to discuss about chapter 1. So in chapter 1, in summary, we talk about what is the universe, what is astronomy, and astronomy is a science study the universe. We also talk about the process of scientific method, as well as the new units we use to describe the distance in space, in universe, or in astronomy, like light year astronomical units. And we talked about the universe in large scale, what is beyond the Earth, the solar system, as well in small scale, what atoms are basic building blocks of the universe. And finally, we talk about the time scale of the universe. If we fit everything of history of the universe in a calendar year, among the relatively what time everything happened.